Variability. In this lecture, we're going to go over what variability is. We're also going to go over how to define and compute range, the simplest way to determine variability. Different ways we can compute variability. The more standard ways or the more statistical ways are definitely variance and standard deviation. So we'll go over how to determine variance, sum of squares, standard deviation for both a population and a sample. Okay. Please don't forget from lecture 1, 2, and 3. So lecture 1, summation notations, lecture 2, all your scales of measurement, and lecture 3, big thing from lecture 3, all about your central tendency, so mean, and how to determine averages, things like that, and then also median. Okay, so what is variability? Variability can be easily described as just a quantitative distance, right? So what is, how far apart, how close together are your scores, right? So it's a quantitative distance, it's a measurement, and it's based on the differences of your scores. Okay, so you the statistician, you the scientist, the psychologist, the person gathering all the scores, how far apart, how closely together clustered are your scores. It's the spread of the scores or the distance of a score from the mean. Again, so go back to the last lecture when we went all about determining your set of scores, then determining your frequency distribution, and then from your frequency distribution, determining your mean or your average. Then, this is just one more step on top of that, determining the variability is how far apart are those scores, or how tightly clustered together are those scores. Okay, so what is the purpose of variability? One, it definitely does describe the distribution, clustered versus spread out. It also measures how well an individual score, so one raw score, represents the distribution. And this is where it starts to talk about, okay, well, if it's all over the place, right? If it has high variability, one score really probably won't accurately represent a lot of the other scores. The probability that you're going to just randomly select a score that is going to really showcase like, oh, this is the average, or this is going to really represent it, the bulk of my data probably isn't going to be. But if it is spread tighter, right, if it's really clustered together tight, yeah, you have a much greater probability or chance of that one score really representing well. So that's where what the variability is kind of, it's like what its highlight is, right? Why we get so excited about knowing what the variability is. Okay, so like I mentioned, it does differ slightly if we're talking about a population versus a sample. So what we have here is just that distribution, right? What we're looking at here though is population, right? So we have a lot of data on things like blood pressure and IQ scores, and in this case height and weight, right? So if you take a look at adult height in inches, right, you see how the scores, that distribution curve is really squished together, right? It's tighter, it's narrow, it peaks higher and comes back down, right? So the height of adults, right, so you have 58, and remember, think that 60 is 5 foot tall, right? And 72 is 6 foot tall, right? So the bulk of adults in this population, right, fall somewhere between 58 inches and 82 inches, right? Versus the weight. The weight, you're going to have much greater variability, meaning the scores are going to be much more spread out. So when I said, please don't forget anything from last lecture when we talked about frequency distribution, right? The y-axis, the up and down axis, right? The frequency is the taller it is, the greater the frequency, right? So in the adult weight in pounds there, right? So you have some that weigh around 110 pounds, and then more that weigh 140. And then in this one, it's only one mode, one mean, being 170, right? And then again, it kind of starts tapering off. When we know the mean, right, because we have so many data points, we have a population, okay? when we're dealing with a sample, those can be a little bit different. Okay, regardless, we have 4 ways we can measure variability: range, interquartile range, variance, and standard deviation. Okay, let's start with range. So range is the simplest and the easiest way to measure variance or variability. It's just the distance covered from the scores in a distribution. You take the smallest, you take the largest, and you say that's my range. Okay. So for example, if my dean or my vice president of academic affairs comes to me and says, what's the range of your last test that you gave? And I say, okay, well, let's take a look here. I just gave my first test for the semester. And I had some people just, they totally forgot that we had the test coming up, and they got a 0. They didn't take it, right? And I had a group of students that they had study groups, they went to tutoring, they knocked it out of the ballpark. They got 100%. So for this test, my data set, my scores, right? My range would be 100, from 0 to 100. Are you already starting to see how this have some issues, right? The range in this case is wild. Yes, for continuous variables, real limits are used, right? So the formula for a range is the upper real limit for whatever your maximum score is. So again, X is still going to be used for our scores, minus the lower real limit for whatever my minimum score was, in this case, 0. Okay. Again, it's only based on 2 scores. Not all scores were presented. It's implied that everybody else's scores in there fell between 0 and 100, which is true, which is accurate. I'm not lying. Some students in my class scored 89 and 27 and 32 and 99, right? But it definitely is an imprecise, unreliable measure of variability. Okay? Versus if I gave a test and it was the final and I was like, people, show up to this, like you have to take this test, right? And I was like, I'm gonna give out gift cards, like please show up, like the person who shows up first will get like a gift card. I'm gonna hand out cookies and I will text you and call you and hound you to show up, and like I know how to get you there. Everybody shows up. And we had study sessions, and like I know you know this material. Right? Everybody shows up for the final, and you all do amazing, right? And the range now for this final is like between 95 and 100. Okay, right? So now, sure, I can give my dean or my vice president of academic affairs the range. I can say, yeah, my range for this final was 95 to 100. So I'm not saying a range is bad. If your variability is very tight, if all your scores are very tightly clustered together, give them the range. But if your variability is very high, if your range is all over the place, like lowest to highest, it's not that precise. It's definitely more of an unreliable way to kind of give variability. Okay, number 2, interquartile range. Okay, ooh, don't like that way that line's there. Okay, interquartile, think quarters, like United States quarters, like out of $1 you can get 4 quarters. First quarter, second quarter, third quarter, fourth quarter. When you break it down by percentage, it does sound like 25%, which would be like 1 quarter, right? 50%, which would be 2 quarters, 75%, 3 quarters, and then 100%, which would be 4 quarters or like $1, right? Yes, they do call them first, second, third, and fourth quartiles, respectively, depending if, so you would say first quartile for your 25%, second quartile for your 50%, and you keep going, right? What you do is you divide the distribution in 4 equal parts, depending on what data group you're looking for at that distribution, okay? So if you take a look at this first one there in green, right, so you have a clean graph there, right? So you have the median. So again, think back to our lecture from our last lecture. So you have the median, you have the 25%, you would say that's the first quartile. Okay. Now, how you present the data, it's usually the lowest quartile. Okay. When you read it, you can also say it's the upper quartile. It's okay, just read how the researcher is presenting the data. Okay. If you take a look at the graph there on the right, you can also have it not as clean, like 25, 50, 75, 100. Okay. You would still have that middle distribution of 50%, the bottom 25%, and the top 25%. But you can also see how they can break it down even further. So you can be in the top 17%. You can be in the top 3.2%. Okay. But at this point, we're just going to keep it simple with interquartile ranges. So the interquartile range, the acronym is IQR, is the distance between the scores, your X values, corresponding to the first quartile, notated as Q1, and the third quartile, notated as Q3. Scores fall in the middle, 50% of the distribution is going to be more like your average. This is the interquartile, or the interquartile range. Again, IQR. Let's do some defining. So defining variance and standard deviation. The most common and most important measure of variability is standard deviation. In a lot of textbooks and a lot of academic journals and a lot of conferences you're going to start attending, you're going to hear it as SD or S. Absolutely, you're going to hear it as standard deviation. Okay. Standard deviation is the measure of the standard or average distance from the mean. Okay. Again, mean means average. Okay. You can drill it down to one person, to one score. You can also use it as a group. Okay. So if I just took my SATs, okay, I can say how far off from the average did I score? Because that's how the SATs are delivered. That's how your score is determined. Okay. Now, just like IQ scores, we don't say you're perfectly average, we're going to give you a 0. Because again, humans don't like to hear 0, because if we give average humans a 0, that means we have to give below average. If you score below average, we have to give you a negative number, and then people would really get upset. Okay, but again, when we measure you against the standard deviation, what we're measuring you against is against the average. Okay, so a measure of the standard or average distance from the mean. You can do it on an individual level, me. I can also do it compared as a group, right? So if I went to North Valley High, right, and I'm a principal, and I go to like a superintendent's meeting, and I have to stand up and I have to report as a principal, how did my students, my graduating class, do on the SATs last year? And they go around to the different principals, and North Valley High, they call my high school, and I say, okay, I'll stand up and report for my high school. I can also give that score set a standard deviation. Okay? The calculation differs for a sample versus a population. Variance is a needed component, is needed for both. It's a companion concept for both, right? And variance is not the same thing as standard deviation. It is a trail that you use, it's a concept that you use on your way to get to standard deviation. Okay. So let's define variance and standard deviation. And I'm going to run you into a brick wall here. I'm going to run you into a dead end on purpose to show you why we can't go this way, because students want to go this way. I'm going to run you in that brick wall, and then I'll show you how to actually do it. Okay. What students want to do is just say, okay, we're going to determine the deviation. And again, the deviation is just that distance from the mean, right? What's my score and how far away from the mean am I? Okay. So what students want to do is just, okay, find some of the deviations. Again, I'm just going to find, well, how far away from the average am I, or the average deviations. And again, if you strictly do that, you're going to run into two different problems. one, the deviations sum to 0 because mean is that balance point, right? The average. If you sum it, you're always going to get to 0, right? So if I take all my scores above the mean and all my scores below the mean, I'm always going to get 0. So I need to have a new strategy, okay? What I need to do is I need to remove negative deviations. Now think back to your Algebra 2 or your trig class, right? How do I remove negative deviations? Well, the easiest way I can do that, or the quickest way I can do that, is just I square it, anything, right? So if I was negative 2 standard deviations away from the mean, or if I was below average by 2 or whatever, right? That's fine. Just take away my negative. Just make me be away from the mean, okay? If I take away the negative, I can just look at the number or the distance I'm away from the average. Another way you can look at that is if we're both 2 miles away from home, Distance doesn't have a negative measurement to it. You can't be negative 2 miles away from home. Okay? If I'm truly trying to find how far away every score is from the mean, get rid of the negative. Just treat it all like distance. Okay? If you're 7 miles away from home and I'm 3 miles away from home, we're both far away from home, but don't make me be negative 3 miles and you positive 3 miles. No, we're just both different miles away from home. So remove the negative. And the quickest way to remove the negative is just square everything. Okay? So number 1, square each deviation score. Okay? After you square it, add them up. So sum it. And that's where we get the idea of sum of squares, or SS. No, it's not Hitler's army in World War II. I know it's the same acronym. Okay, so SS, sum of squares. Then you're going to take the average of the square deviations. Yes, I'm going to show you it mathematically. I'm just kind of walking you through the language right now. The mean square deviation is now known as variance. So remember how I said variance is like on our trail to finding standard deviation? Okay. So yes, variance is fine, but what we really want is we want standard deviation, because no one really talks in variance. We all talk in standard deviations. So variance equals the mean, or the average, of the square deviations. So all you have to do now is just take the square root of it, right? Like that little equation down there. So standard deviation is just the square root of that variance. Okay, so step 4, you compute a measure of the standard or average distance of the scores from the mean. Keep in mind, variance measures the average squared distance from the mean. Again, we're not to our goal yet. It's not quite our goal. Yes, you are adjusting each score by squaring the distance, but we're doing that so we can get rid of the negatives. You need to get it over the finish line. To get it over the finish line, you just take the square root of variance. Okay. Again, most students like it, their first gut instinct is to say, well, just find this deviation and add the deviations. But again, it's always going to give you a dead end, because if your score is -3 and my score is 3, if we start walking together, we're going to get to 0. Right? Square each deviation, regardless of the sign. Then find the average of the squared, again called variance. Once you have variance, just take the square root of it, and that will give you your standard deviation. This is what it looks like graphically. Here you have just a simple histogram. Okay. You know it's a histogram because the bars are touching, they're mushed up next to each other. Yes, you have some gaps in data. You have some people that did not score a 2 or a 3 or a 6. Yes, with a histogram, with continuous data, you can have an average, you can have a mean that is not one of the actual scores. So even though we did not have anybody that scored a 6, our average or our mean, or in this case mu, is 6. Okay. Yes, still the frequency, how tall it is. is the height of the corresponding bars. X is still our scores. Okay. So now we're going to measure variance and standard deviation for a population. SS, again, SS stands for sum of squares. It is the sum of the square deviations of the scores from the mean. I'm going to say that again. SS is the sum of squares. It is the sum of the square deviations, right? So square all the deviations and then sum them up, add them up, all the scores from the distance from the mean, okay? And we have two scores, or two ways we can compute these. You're only really going to use one. One is a definitional formula. It's beautiful, but we never use it. And one is actually like a computational formula. So yes, I will tell you both. A definitional formula is sum of squares equals, and this is sigma, right? So sigma equals, or sigma times x minus mu squared, or sum of, okay. So in the definitional formula, what you're going to do is you're going to find each deviation score. How you do that is you take each score minus the mean. So in theory, what you're doing is you are taking each individual score, and again, for a population, which could be billions of numbers. That's what I'm saying. This is a definitional formula. You're never going to use this. We are not AI. We are not computers. Well, I don't think we are. Jury's still out on that. This would take forever. Then you're going to take that, and then you're going to square each of those scores, and you're going to add them all up. It's a lot of work. Okay, how we actually do it is the computational formula. So sum of x squared minus sum of x squared divided by n, capital N. I have a whole series on videos on how to actually run these numbers. Or linguistically, it sounds like this. You're going to square each score and then sum up the squared scores. Then you're going to find the sum of scores, square it, and then divide by n, capital N. And then subtract the second part from the first. You're going to have to trust me, it is not that hard. This looks like a big hairy equation. It is not that bad, I promise. You don't think so, you don't trust me, but just trust me on this one, okay? Please keep in mind, sum of squares is not just adding up all the scores that you squared. Sum of squares is not just taking all the scores and then squaring like your total number that you add all the squares up. And also taking all of your scores that you squared does not equal your scores added up squared. Okay, meaning, listen for the pause. When I say sum of x squared versus when I say sum of x squared. Okay, I know it sounds like I'm saying the exact same thing, but I'm not. Okay, so listen again. Like, close your eyes, that helps. Sum of x squared is not the same thing as sum of x squared. And again, I have a whole video that ad nauseum you will know the difference, what that is. At this point, just know they are not the same thing. Okay, formulas and notations. The formula for population variance and population standard deviation looks like this. Okay, so variance equals sum of squares divided by n, capital N. Standard deviation is just the square root of that. Remember how we said, yes, we love variance, yes, we want to find variance, and no, we're not done when we have variance. Once you know variance, throw that number in it, and then just take the square root of it. Okay. Variance is the average of square deviations. So yes, we identified population variance with a lowercase Greek letter sigma squared. So sigma is at that little kind of fancy O with a curly Q up top. squared. Standard deviation is just the Greek letter sigma. Just a little like circle with a curly cube top. Okay. So in addition to knowing all these new formulas, you're also going to learn a little bit of Greek, right? At least the letters, at least the alphabet. It's fun. It's fine, right? They're beautiful little letters. So mathematically, right, we use Arabic, right? So we use the Arabic numbers in America. And in statistics, when we start writing it like with language, we're going to use Greek letters. So it does help to understand, at least mathematically, when you see the Greek letter sigma just by itself, you know we're talking about standard deviation. So when I said at the very beginning of this lecture, standard deviation, you're going to see SD, or sometimes just S, or sometimes they just write out standard deviation. Mathematically, when you see someone actually like doing an equation, they're probably going to use the Greek letter sigma. And when you're calculating variance, you use sigma squared. Okay, really quick, true or false? The computational and definitional formulas for sum of squares sometimes give you different results. No. It's the same thing, algebraically. And so they're going to give you the exact same results. And use the computational one. Because the definitional one is more like theory. You're going to turn yourself nuts using that one. Okay, true or false? If all the scores in a data set are the same, the standard deviation is equal to 1. So if all the scores in a data set are the same, the standard deviation is equal to 1. 0. Remember? Again, think number line. In a population, definitely, but also in a sample, all the numbers on the left-hand side and all the numbers on the right-hand side, what divides in the middle? 0. All right, so you get a number line. All the numbers on the left-hand side is like -1, -2, -3, all the way to like negative infinity. On number line, on the right-hand side, it goes like 1, 2, 3, 4, all the way to infinity, positive infinity. I know there's no such thing as positive infinity. Okay. One multiple choice. The standard deviation measures the sum of square deviations, standard deviation of a score from the mean, average deviation of a score from the mean, average square distance of a score from the mean. And what do you think? What do you think that standard deviation is trying to measure? You know this, right? I keep banging this one over and over again. The standard distance of a score from the mean. That's the whole job. Okay. We're going to talk about samples now. So measuring variance and standard deviation for a sample. So same thing. You're going to try to draw general conclusions about a population based on limited information from a sample. Because we have limited information, it's not going to be as accurate, but we still need to do it because, to be frank, most of the time we are dealing with a sample, not a population. And samples differ from a population. They definitely have less variability because they're smaller, right? And computing the variance and standard deviation in the same way would definitely give a more biased estimate, right? So we have to do just something a little bit different, right? Okay. Just a quick example here, right? You're probably not going to ever do a population on, what is this one? Who knows what this one is? We'll go IQ scores. Oh, height, sorry. Height again. We love height. Okay. You are much more likely to do it on a sample, which is fine. Again, there's nothing wrong with that. You are going to have a sampling error, which I know we haven't talked a lot about yet. And it's okay. We can still run variance. We can still run a standard deviation. It's just going to look a little bit different because we're dealing with a sample versus a population. Okay, so here's our formulas. See how it looks just a little bit different? So you still have your sum of squares, SS. You compute sum of squares just like you did before, just like you did for a population. The formula for a variance now has n minus 1, and n minus 1 helps mitigate those errors of like sampling errors, also called degrees of freedom. Okay, we'll get into that in a second. You are now going to use a little bit slightly different notation. Instead of using that beautiful like circle with a little curly Q on top, or sigma, you're now just going to use a little s. And think back to last lecture, instead of a big N, little n, because it's a sample. Okay, so linguistically it sounds like this. Variance for a sample equals sum of squares divided by n minus 1, or degrees of freedom, or df. And again, it'll all be the same, just might look a little bit different. Standard deviation, or S, for a sample, equals the square root of that. So same exact muscle you're going to use, right? So remember how we just took the square root of our variance for population? Same exact thing for standard deviation for a sample. Just take the square root of variance. So here we have another histogram, but now it's a sample for 8 people. Okay. Our mean, not mu, 6.5, right? And little n, not big N, 8. Okay. Again, we can definitely have a histogram for a sample with missing data, right? What are we looking at here? We don't even know. Number of siblings, we'll say. We just didn't have anybody with 8 siblings in our group. We had someone with 11, someone with 3. The height of the bar still corresponds to the frequency. So we had 2 people that had 7 siblings, 1 person that had 9. So it works for a sample just like it works for a population. Okay. Sample variability and degrees of freedom. Degrees of freedom, I'm going to start from the bottom, is the number of scores in the sample that are independent and free to vary. At this point in these lecture series, just know that degrees of freedom, as symbolized by DF, and it is like a slanty DF. So think like if you're handwriting it, it's like DF, like a slanty, like you're writing it like italic. For a sample, is just n minus 1. Yes, that will change, but right now it's just n minus 1. So whatever your sample size is, minus 1. When we're talking about population variance, the mean is known, so the deviations are computed from a known mean. So you're a lot more solid, right? With a sample, the population is unknown. So using the sample mean, it restricts it. It doesn't give you as much like solid footing, if you will. So your variability is going to be a little bit, well, wonky. I know it's not a word in academia, but it's going to be wonky. It's fine because we know we deal mostly with samples versus populations, right? So we just put in the degrees of freedom to allow us to work with samples. Okay. Quick clearing check. A sample of 4 scores, so n equals 4, has a sum of squares of 24. What is the variance? So I kind of did this to you last lecture when I gave you 2 of the 3 bits. I messed around with the equation just a little bit. So sum of squares, 24, n equals 4. What's the variance? Remember, if you know 2, you can always find the third. Okay. True or false? A sample systematically has less variability than a population. So again, variability is how spread out or tightly clustered together are your scores. Because you have less chances, because you have less numbers. Absolutely. Okay. True or false? The standard deviation is the distance from the mean to the farthest point on the distribution curve. True or false? The standard deviation is the distance from the mean to the farthest point on the distribution curve. What do you think? So here's the thing. The standard deviation is only going to go from the mean to approximately halfway to the most extreme score on either side. Okay. Sample variance as an unbiased statistic. Okay. Unbiased estimate of population parameter. Yes, definitely. Okay. So the average value of statistic is equal to the population parameter. I'll say that again. The average value of statistic is equal to the population parameter. The average value uses all possible samples for a particular sample size, n. Okay. The corrected standard deviation formula, dividing n by n minus 1, also known as, right, degrees of freedom, at least in the case for this lecture, produces an unbiased estimate of the population variance. It approximates it. It gets us closer, right? It recognizes that, yes, we are dealing with a sample. Totally okay. Again, in most research and most studies, we are dealing with a sample. And so that n minus 1 gets us closer to estimating or approximating an unbiased sample. Okay. When we're dealing with a bias estimate of a population parameter, then we're going into systematically overestimating or sometimes underestimating the population parameter. In certain instances, in certain research studies, this is also okay. As long as you're recognizing why you're doing it, this actually could be part of your independent variable as the researcher. Okay. Variance and standard deviations. Means and standard deviations are particularly useful in clarifying graphs of distributions. Absolutely. Okay, means and standard deviations together provide extremely useful descriptive statistics for characterizing distributions. They give us an extra layer of information, an extra layer of what's the next step we need to take, right? An extra layer of critical thinking, an extra layer of creative thinking, an extra layer of, did you think of this? Okay. So take a look at this frequency distribution, right? For both the population and the sample, so the population left-hand side and the sample on the right-hand side, it's easy to represent both the mean and the standard deviation. Again, the vertical line is in the center. It denotes the location of the mean, or the average, right? So you have the mu there, and the first one is the mu is the 80. The standard deviation is 8. Okay? So if my score was 80, my standard deviation is 0 because I am perfectly average. I don't deviate anything from the average. If I deviate one standard deviation above the mean, I have a score of 88. Because I know that distribution is perfectly symmetrical, the right side looks like the left side. If I deviate one standard deviation below the mean, I have a score of 72. Okay. So when we're dealing with standard deviations, it is an actual score or a representation of a chunk, right? Okay. The same is also with a sample. Okay. We're not going to get too much to this, but I can also transform a scale, or I can norm a scale, meaning I can transform a scale of scores and I can normally distribute them. And this is where it kind of gets very exciting. I know you don't think it is, but it does. This is when we can take SAT scores and IQ scores and we can transform it into a scale. So kind of a little preview there. Okay. With descriptive statistics, so standard deviation describes scores in terms of distance from the mean, just like we did with descriptive statistics, right? Yes, we can describe an entire distribution with just two numbers. If I just give you the mean and the standard deviation, you can tell me what it does, what kind of shape it has, what you can tell me a lot, right? So when we talk about descriptive statistics versus inferential statistics, yes, by just 2 scores, by just 2 numbers. Okay. Okay. The goal is, here's inferential statistics. So variance is more with inferential statistics. So the goal of inferential statistics, right, is to detect meaningful and significant patterns in research results. It allows you to tease out meaning. It allows you to propagate future, right, a little bit. Variability in the data influences how easy it is to see patterns. So high variability obscures patterns. Low variability, you're a lot more predictable. Okay. With variability is often classified as error variance, and the higher the variability, the higher the error, or the less likely you are to be able to predict, right? Okay. And here's some high versus low variability. Okay. The major takeaway with variability: statisticians, when we seek to learn like what variability is or what this data set is telling us, is, can I determine how far apart my data sets fall? Or how close together are my scores clustering? Okay. It's okay. And again, like I've said in a few different lectures now, one is not good or bad, right? It's depending on what you're trying to learn from your data. Sometimes it's really good if your data is all over the place. Right? Sometimes it's really good when your data is really tightly clustered together. It depends on what you, the statistician, is trying to learn from your research.